In the last lesson, we looked at the collapsing atom paradox. It was a problem with the Rutherford atom. And remember, in a Rutherford atom, you get a nucleus in the center, and you've got a little electron moving around it. It's orbiting it like a planet orbits the sun. And the problem is when you've got an electron that moves around like that, it's an oscillating charge. And according to what we know about electromagnetic radiation, that should produce electromagnetic energy. It should beam it out of the atom. And as it does, that electron, as it beams out electromagnetic radiation, it's going to lose energy and it's going to spiral into the nucleus until the atom collapses. So if you really had Rutherford atoms, you would see a sudden burst of electromagnetic radiation and the atom would be collapsed. But we don't see that. You can get atoms to emit electromagnetic radiation, but first you've got to kick some energy into them. You can put the atoms in a tube with very high voltage. You can use a flame, you can use plasma, you can use a spark, but if you kick some extra energy into the atom, it'll kick it back out again by emitting photons, by emitting light. And it's interesting how it happens. Take a look at these pictures that I have here. Here you've got different metals. We got lithium, sodium, potassium, rubidium, cesium, calcium, strontium, barium, copper, thallium. And they're emitting different colors of light, very different colors. Why? Why do different elements emit different colors? Well, different colors correspond to the emission of different wavelengths. And we could measure those wavelengths, and it might tell us something about why these atoms are all different from each other. This is telling us something about the internal structure of the atom. And this is what we'll be looking at in this lesson. So how do we look at the wavelengths that are coming out of a light source? You can use a real simple apparatus called a spectroscope here. And the spectroscope has got a light source here, which in this particular case is just an old-style incandescent bulb. What's important is that what I have here is a very dense material that's heated up quite a lot. And it's going to produce white light, which is a mixture of a lot of different wavelengths of light, a lot of different colors of light. I am going to focus the light that's coming in using a slit. So I have a block here with a little slot cut through it, and that's going to give me a very narrow beam of light. And then I'm going to hit some kind of a device that bends different wavelengths of light at different angles. Now, a prism is one way to do that. If white light passes through a prism, the red light does not get bent as much as the violet light does. So it has something to do with the wavelength. The longer the wavelength, the less it gets bent when it goes through the prism. The shorter the wavelength, the more it gets bent. So you're essentially separating out the different wavelengths of light that are all mixed together in white light here. And you don't have to use a prism. There are some other things that you can use. One of them is a diffraction grating, which is a piece of plastic that has very fine lines ruled across it. And it will do the same thing. It will reflect different wavelengths of light off of itself at different angles. Now, let me just mention that this kind of explains why the sunset is red and the sky is blue. When you were looking up at the sky, say you're down here, you're seeing blue and violet light being reflected back down towards the ground. So the sunlight is coming in up here and it's getting scattered down towards the ground here. But around sunset, you've got a kind of straight line view of the sun. And all of the blue and green and yellow and all the other colors are getting scattered out of the light. And you're you're seeing the red. So when I put an element lamp here, what am I going to see? Let's look. Here I've got a tube. It's got hydrogen in it, and I am passing about 1,000 volts of potential between these two metal caps on the end. So there's a lot of electrons rushing through the gas, and as they rush through the gas, they strike the hydrogen atoms, and they kick some kinetic energy into the hydrogen atoms. So the hydrogen atoms get into a high energy state, and they want to get back down to relax back down to their normal state. We call it the ground state. And in order to do that, they have to emit light. When you see a hydrogen lamp come on, it's just about this color. It's kind of a purplish red color. It's not white. And we pass it through the slit here into our dispersal device, our prism, which can be anything that bends different wavelengths of light at different angles. And we see something different from what we were seeing before. Before we had white light, which was a mixture of a lot of wavelengths, all wavelengths. And here we're only seeing certain wavelengths and not others. There are a lot of gaps in the rainbow here. There's red coming through, there's sort of a turquoise color coming through, there's blue and a purple color coming through, but nothing else is coming out of the hydrogen lamp. And if I look at this film plate on the end where the light is striking, I see something like this. I can measure the wavelengths of light by where they are on the film strip. Since different wavelengths get bent by different angles, I can calibrate this thing. And I see there's always, with hydrogen from anywhere, from any source, a line at almost exactly 656 nanometers, and it's the same no matter where the hydrogen is, whether it's here in my lab or whether it's on another star. That hydrogen from anywhere is going to produce a 656 nanometer line. And then there's a 486 nanometer line, a 434, and a 410. Why those numbers? And why does hydrogen produce that? What if we try another element? Turns out that every element produces its own spectrum, its own pattern of lines. And that pattern of lines is distinctive for that element. So whenever you see a 656 nanometer line, a 485 nanometer line, a 435 nanometer line, a 410 nanometer line, that's hydrogen. Nothing else has got that pattern and those particular wavelengths. Take a look at the helium spectrum. It's got some lines in it that hydrogen doesn't have, and its lines are in different places than they are in the hydrogen spectrum. In fact, helium was discovered on the sun before it was discovered on Earth. Helios is, the Latin word for the sun, and they saw this pattern of lines in sunlight, and they said, this is not a pattern that matches any terrestrial element, so we've just discovered a new element on the sun. They did discover it later on the Earth. It's mixed in with natural gas, for example. That's one place that you can find it. It's produced by radioactive decay of minerals, so you can find it on the Earth, but they found it first on the sun with this. And that's kind of an important point. We're discovering all these exoplanets now. It is going to be possible for us to look at their atmospheres someday with spectroscopes. Once we get some technological obstacles out of the way, we'll be able to focus a spectroscope on their sunlight, their starlight shining through their atmosphere. And we will be able to see what is in the atmosphere there. We'll be able to see if they have oxygen in the atmosphere from all this distance without ever going there. Here's a neon spectrum. You've seen neon signs. You're essentially looking at a neon emission spectrum, but when you look at it with your eyes, you're seeing all of the wavelengths blurred together. So notice there's a lot of red and orange and yellow lines. So when you look at an actual neon sign, it's always this sort of orangey color. Here's another one that you probably have seen. They have these sodium lamps. They're street lamps. They're very cheap and they're very bright. There's a 589 nanometer line in sodium that's extremely bright, and it's kind of monochromatic almost. You notice things look, colors get washed out under this light because you're only seeing things in sort of this brassy yellow-orange light that sodium lamps emit. And here's mercury. Here's a mercury spectrum. And it's got this real strong line down here at 545, 546 nanometers, and it gives everything a kind of a greenish tinge under fluorescent lights. Fluorescent lights have a lot of mercury vapor in them. So why are these different atoms producing different patterns and lines? What is different about different atoms? Again, this is a clue about the internal structure of the atom. Now, here's a slightly different experiment. We've been looking at emission spectra. These are electromagnetic radiation that is being emitted by atoms that have had extra energy put into them. What happens with cold atoms, just atoms without a lot of energy kicked into them? What if I take a white light source, like an incandescent bulb will work, and I shine it through a tube that contains a gas with an element in it? Well, white light is going through the slit here, but I don't get a nice rainbow like I got without that hydrogen gas there. There are some colors that are knocked out of the rainbow after it goes through the hydrogen gas. Which colors? And what does this have to do with the emission spectra? Is there any relationship between this spectrum and the emission spectrum? We're going to call this an absorption spectrum because what is happening is that the rainbow is going through the hydrogen, and the hydrogen is absorbing some of the colors. Some of the wavelengths, the colors, are being knocked out of the rainbow here. Now, if I look at the film strip, here's the film strip for an emission spectrum, and here it is for an absorption spectrum. And what you're seeing is the colors that are knocked out here exactly correspond to the colors that you see in the emission spectrum. So when you're kicking energy into the atom, it's emitting it at these particular wavelengths. There are 4 in the visible range. And when you look at an absorption spectrum, you're seeing a rainbow, a continuous spectrum, with those particular colors knocked out. They'll appear as dark lines. It is pretty interesting that you can point one of these spectroscopes up at the sun, and you can see dark lines in the solar spectrum. And some of them correspond to iron. So there is some iron in the outer atmosphere of the sun that is absorbing some of the white light coming from the sun. And you can see that you have all kinds of potential for analyzing elements in different samples this way. You can take any sample, vaporize it, get it, kick some energy into it, look at its emission spectrum. Or with cold atoms, like the atoms maybe in an exoplanet atmosphere, you've got white light behind the atmosphere and you've got the exoplanet here, and we look at the light that's shining through, we can see if there is a pattern of dark lines that corresponds to oxygen and detect oxygen in that other planet's atmosphere that way. And even be able to tell how much oxygen maybe from how much light is being absorbed at those particular wavelengths.